Welcome back, everybody. I wanted to give you a quick overview of what we are going to do today and what the plans are for the rest of the semester. So the idea today is to actually wrap up the discussion on recurrent neural networks. And if you scroll down on the README page, which we have here on the GitHub address, the main GitHub address of the course, you will see now that the kind of plans is to perform this summary, and then Atle, who you met last time, he will be discussing with you project number 2. So the kind of plans is that I'm not going to use more than half an hour, and then we can use the rest of the time on project 2. And on March 21st, we can also dedicate time to project 2 instead of us actually bringing in new topics. The next stage is that on March 28th, before the Easter break, Anders Kvellestad will start with an overview of Gaussian processes and Bayesian statistics, and this will continue till roughly the beginning of May, and that will end our sessions. And the topic today, as I mentioned, is about recurrent neural networks as a kind of summary. One thing which I did is to add some material about autoencoders, if you're interested in that, AE. And there are some lecture notes which are actually pretty good. I don't want to add more complexity to the course here because you have already enough. And solving project number 2 with either neural networks or recurrent neural networks, if you're dealing with a differential equation path, then that should be enough material. If you wish to explore autoencoders and the general adversarial networks, which would actually have taken us at least some 3-4 more lectures, I rather recommend that this is something you can study by yourself if you wish to. Else, we are more than happy with including recurrent neural networks in project number 2, if it fits. Only if it fits. So I will leave this up to you, and that means that we will spend a large fraction of the time today to discuss project number 2. So Atle will lead these discussions, and we will do the same thing next week. So next week, there is no lecture, there's only project work. Okay, so the material which you find here for these 2 weeks, from weeks 10 and 11, March 6th to 17th, the material contains a little bit about convolutional neural networks, which we discussed last time. And then if you scroll down here, you will find the start of the discussion for recurrent neural networks. So if we just scroll down and just try to remind ourselves a little bit about what we did last time. So the networks which we have seen previously, in terms of a feed-forward neural network, you would have some input, and this input is fed into a set of hidden layers, and then it produces an output which is compared with the target values which we want to reproduce. And then we have the recurrent neural networks where we actually, when we open them up, because here we can have an input at every time step or every stage. So T doesn't need to represent a time. It could represent a specific stage in the data set which we are looking at. So if you're dealing with natural language processing, this could actually be the next phrase in a long paragraph. In our case, and for most of the applications which you guys are going to look at, it's often a time series. And this could be a time series generated from a differential equation, or it could be a time series which comes from some specific measurements, just to give you some examples. Now, the graph which you see here is then typically opened up, and it means that we would have some input at a time t0, and this continues to a final time. We have outputs which we produce. There may be some external probe which feeds into the network, and this external probe could be an external force which acts on the system, or it could just be some specific input. It could be a laser being applied to the system which you have. And then we are trying to model the interaction of this external probe with the system, and that produces an output at every time step. And that's compared with some kind of measurements or target values. And these hidden layers here, they send their input to the next layer, to the next layer, and so forth. So that gives a pretty strong memory in the calculations. And if you look at it, you can open this up. So you could have a single layer, or you could have many layers. And that clearly complicates the training, because you would have to use the back propagation inside here, train all the weights and the biases, etc., etc. But you can make these networks actually more and more dense. So these are figures which I've stolen from Sebastian Raschka's book. And it's a book called Python Machine Learning. It's actually a pretty good book. And then if you now look at the inputs here, what happens is that each hidden layer receives an input from the previous stage, as you can see here. So this feeds in here, and then it receives an input from the external probe. As an example, that could be a laser, which is acting on a specific system, and then produces a specific output. Again, you can have a single layer, or you can have a multiple layer. When you then train these different models, you can have different sequences of modeling tasks. You can have many inputs to just one, or you can have one to many. You can have many to many, like the network which we saw here. And again, you can have other types of structures. So there's a lot of flexibility on how you train these kind of structures here. So you need typically to specify the initial activity states of all the hidden and output units. And these are normally fixed by some specific random numbers. And then you have weights and biases. So if we scroll down here, you would then have weights which connect the input layer with the hidden layer. There are weights which connect this hidden layer with the next hidden layer. And there is a set of weights which connect the hidden layer with the output at a given stage. And these weight matrices contain then the unknown parameters which we need to train. And these weight matrices would typically then be given by, in this specific case, you would have an h of x, which now modulates the input from the input part. There is an HH here, which then takes care of the connection between the previous layer. And then there is obviously a bias. This is now fed into an activation function, and it produces an output here, which is H of t. This output H of t is now sent in here to the next stage, but it also sent to the output layer. So that means that you have an output layer, which now produces this quantity here. This is then used in turn as an input to the output layer. So this is this z of y, and it's multiplied by this weight matrix plus its own bias. And then there is a new activation function or modulation function, which then produces the final output. And this is the number which is being compared with the target value at a given stage. And the way these networks are trained is by something which is called back propagation through time. So you would typically compute the different cost functions at each stage, and then you evaluate the total cost function as a sum of all the different stages or time steps, if we prefer. And the back propagation through time algorithm is actually described in this article here by Verbos. And in the back propagation through time, what you need to do then is, again, to take the derivatives with the chain rule, and that gives you the derivatives for all the gradient components for all the weights. And similarly, you can also get the gradients for the biases. And essentially what is done here is to use the chain rule in order to calculate the different weights and biases and their derivatives. And it's normally computed as a multiplication of adjacent time steps, as it's shown here. That's the basic rule which is being used then. And that computes when it computes this, as we discussed last week, this can lead to this problem of so-called vanishing gradients. And with that, when you have this problem of vanishing gradients, one of the standard recipes is actually to clip the gradient, as we discussed last time. Now, when you look at this setup here, as we discussed also last time, if we just go back to this image which you see, this is a process which cannot be parallelized and computed efficiently, because it's a very sequential process, and each result depends on the previous results, which means that this is a memory-intensive process, because we need to store the weights and the biases, the outputs from the hidden layers at each time stage. And furthermore, when you now perform these operations, there's always the risk in the training that the gradients can become very large or that they can vanish. And these are things which one has to look after. Now, there are ways to change this, and one of the ways to change this, instead of feeding in from one layer to the next one, hidden layers, you would only feed from the output into the hidden layer, and then the next output to the hidden layer, etc., etc. And this is something which can allow for a possible parallelization and a more efficient calculation, but the price you pay for that is a loss of memory. Now, there are ways to try to cure this, and one of the ways is actually to use something which is called long short-term memory, which I just wanted to mention. And these are actually designed to remember values for a long time without paying the price of a large storage of different quantities at each time stage. So a quick summary of the RNNs. So the recurrent neural networks have, in general, there's no probabilistic component in a model. With a given fixed input and target from data, then these RNNs learn intermediate association between various layers. Inputs, outputs, and internal representation are all real valued vectors. And in a traditional neural network, it's assumed that every input is independent of each other. But with sequential data like the one which we have here, the input at a given stage t depends on the input from the previous stage. Now, when you are solving differential equations, if that is something you would be interested in project number 2, when you first solve it with ordinary neural networks, you will actually have to suffer from the fact that each input is designed to be independent of each other. But in our case, we do actually have inputs which will depend on the previous stages. And you will most likely see that a recurrent neural network is more efficient than the standard neural network in solving differential equations, if you wish to venture along that path for project number 2. So the typical RNN has weight matrices U, W, and V. They connect the input layer at the stage T with a hidden layer, the previous hidden layer with the new hidden layer, and it connects with the output layer. And this is basically the operations you need to deal with. And in the feed-forward stage, you would typically have a tanh function, which is used to modulate the output from the hidden layer, which is then fed in. So that will contain this matrix U times the input, the matrix W with the input from the previous layer. And then it produces an output, which is modulated with a new function. And that new function can be a sigmoid, a softmax, a ReLU, and many of the other activation functions which we have seen before. And the training is done again by an application of the chain rule, but now the chain rule being propagated back in time. And that's called the propagation, the back propagation through time. Now, one of the things which we can look at now is to look at this long short-term memory, which is also an approach which has been used in order to reduce memory requirements and at the same time keep a memory of what is happening. So that uses what's called a memory cell for modeling the long-range dependencies, and also avoids the vanishing gradient problems. Because remember now that the vanishing gradient problem, if we go back to what we discussed last time, arises from the fact that we have a product of all these derivatives. And that can quickly lead to an exploding gradient or a vanishing gradient. So this LSTM is meant to also circumvent the problem of vanishing gradients. So they are normally designed memory cells with the specific units. And we have different cells like the forget cell, the output cell, etc., etc. So what I'm going to show you now is actually a quick overview of how you would actually set up this long short-term memory cells. This contains lots of technicalities which we will not cover in much detail. So I'm going to change a little bit to some slides which I borrowed from another course here. So let me just find these slides. So when you look at this, you will see similar images in my own Jupyter notebook. So this is something which is capable of modeling longer-term dependencies by having memory cells and gates. So these are normally called gated circuits, and they control the information flow along with the memory cell. So what you will often see now is that the structure here, and this is an image which is taken from the site which you see here, and this is capable of modeling longer-term dependencies by having memory cells and gates that control the information flow along with the memory cells. So you could now think of, even if the networks are connected here, that there are only specific cells which do the memory job. And it's normally set up, and this becomes very technical, and I don't know how interesting it can be. If you wish to study further, there are lots of references on how you can construct these kind of memory cells. So the content of a specific cell contains various gates. There's something which is called a forget gate. There's an input gate. There's a reset gate. And then there's finally the output gate. And you can see here that these gates, one of them propagates information to the next one. And this also sends information to the cost function. And each gates are composed of different transformations, and typically they have sigmoid activation functions. So the forget gate, it determines how much content from the previous cell will be erased. And then there are linear transformations on concatenated previous hidden states. And input are followed by a sigmoid function, which is this one. So that produces an output, f of t here, which is this one. And the sigmoid generates values between 0 and 1. And 0 completely remove info in the dimension, and 1 completely keep info in the dimension. So it means that we will have parameters to train here. So this contains now the information from the previous layer, h of t minus 1, and it contains also the information from the external probe, and there is a bias which needs to be trained. Then, so this is just a way to reduce the dimensionality of the problem, if you think in terms of dimensionality reduction. So you keep a track of what kind of information should be kept and which should be forgotten. And then the so-called new candidate cell, they are created as a function of this ht minus 1 and x of t. So this is your, so you have this forget cell, and now you produce an so-called input gate, which decides how much of the values of the new candidate cells are combined into new cell states. And you have additional functions here, which could typically be a sigmoid or a tanh. These are typical functions which are being used. And there are new parameter biases to train here. And then you have the so-called update cells, and the previous cell states are updated to the new cell states by using the input and forget gates with the new candidate cell states, as you can see from the drawing here. So there's a plus here. This adds information from this f of t. And so you have the forget gate, which are then multiplied with the previous cell states. And then you have the input gate, which is then multiplied with this ct here. And that generates an output. And the output will be based on cell state C of t with a filter from the output gate. and the output gate decides which part of the cell state will be in the output. And that is again defined by normally a sigmoid function. And then the final output is generated from TAN-H cell states, which are filtered by this output from the output gate. And that's the final output, which is then being sent to the next layer and also to the loss function. No, sorry, to the output layer at a given stage. So there's a lot of technicalities going on here and parameters which have to be trained. But the whole idea now is actually that we are reducing the type of information which is being kept. And these cells can appear at each stage, or they can appear at only selected stages. And what they actually do is to keep this track of this information, h of t minus 1, when we then propagate back in time. So LSTMs are networks which are in a way widely used, both to reduce the memory constraints which you have in a standard recurrent neural network with a backpropagation algorithm, and also to keep track of long-range dependencies. Now, the way you can implement this is something which you will find in the Jupyter notebook. So if you go back to that one, nope, not this one, but the Jupyter notebook. So let me find that one again. So at the end here, after this, the discussions of the long short-term memory method, what you will find is a set of, so this just repeats what I said here about the different types of gates which are plugged into this cell. So if we just scroll down here, you will find the Jupyter notebooks which contain applications of recurrent neural networks, and you could actually use these in the solution of project number 2. So the example, one of the first example here is a plain recurrent neural network, where we use what's called a simple RNN, and that's the standard setup, fully sequential with a backpropagation through time. And what I've done here is actually to plug in training data, which are the results of a quantum mechanical many-body calculation at different levels of approximation. So this 42 here stands for a specific number of degrees of freedom, and that produces the energy of the ground state, which is this quantity here. And this is slowly converging towards the value which we're interested in. There's a strong dependence of the number of degrees of freedom we use, and that is this parameter x tot here. So what I want to do now is actually to train on only some of the data here. If you think back to the example we had last week with the sine function, where we trained a recurrent neural network on the first 800 time steps, and then we used the trained network to predict the next 200. So what I'm going to do now is actually to train with less data and use a recurrent neural network to extrapolate. Now, when you're training a differential equation solver, in a certain sense, you're doing the same thing. You're training to some input data, and then you have the output data. And then with a trained network, you would actually like to make predictions for later stages. In that case, when you train a dynamical equation, it means later times. So in this specific case, which we have here, first I need to format the data. This is just a technicality to prepare the data for the recurrent neural network, and this is done here. So it's not so exciting. This is just me transforming the data into the right shapes for applications to a recurrent neural network. So this returns actually the inputs and the outputs to the recurrent neural network. And then, so it takes the original array and prepares it for application to a recurrent neural network. What it contains then is a simple RNN, just one hidden layer in the RNN at each stage. So it has a number of hidden neurons, which I put to 200. It has a, if you're interested, I can explain what these parameters mean. And then it returns the mean squared error as my cost function, and it has the Adam method as the optimizer. So in this specific case, let me just run this one. You can now see an example of a prediction which I'm making with the training set which I have. And in that specific case, which is also useful, is to print the model summary, which tells you the number of parameters which I'm training. And in this specific case, I have something like 40,000 parameters. In this case, you see also that the loss function is getting smaller and smaller for each stage we train. And at the end, I'm going to have a loss function, which is something like 10 to the minus 5, 10 to the minus 6. And if you look at my predictions here, so the orange area is the area which I have used to train. So let me just move this one a little bit. So the orange area here is the training data which I have. Actually, I'm not sure whether this color is orange or not. I have always had problems with colors. So I still can't make a proper distinction between pink and violet, just to give another example, which tells you basically that I'm almost colorblind. So you may not call this area for orange. It looks orange to me. Okay, so the true value is the blue line here. And then what you see, the green one is obviously this is the training set. And then this is the prediction which I'm making. So that means for this specific model, I would actually get a pretty decent training result. And you can also see the standard mean, the mean squared error, which I'm getting is 10 to the minus 5, which is a pretty acceptable result. And you also see that when I train things as a function of the number of epochs, so these are the loss functions, they go gradually to 0 here as I increase the number of epochs. So when I've gotten to 40 epochs, typically in the calculations basically give me a loss function which is 0. Now you can change things. You can make the network more complicated. So the code which you see here takes the same data from above and it adds a second hidden layer. And it changes the number of neurons in the hidden layers. And it declares the activation function of the hidden layers to be a sigmoid function. And the loss function and optimizer can also be changed, but I kept them the same as above. And because I want to do the mean squared error here. And I use Adam as a method. What you will notice here, if I run this case with a more complicated network, and you see now that I have, instead of 40,000 parameters, I have 500,000 of parameters to train. Actually, I end up, when I add everything in the different layers, so the first layer has 250,000, and the next one has 500,000, so I'm getting up close to 750,000 of parameters to train. You will see now that the loss function is not impressive. When I continue now as a function of epochs, this just stabilizes around 0.1 instead of 10 to the minus 5 and 10 to the minus 6, which I had in my previous case. And you will also see now that my prediction here is not very good. So this simply means that you increasing the dimensionality of the network and making the architecture more complex does not necessarily lead to a better result. So you do well on the training, but you do extremely poorly on the prediction, on data which has not been included in the training. So this is just a warning, and you would have to play around, as we discussed earlier, with different architectures, which actually represents the model. There's an application of the LSTM here, which, and also something which is called a gated recurrent unit. There's a link to these options. And in this case, instead of having the simple RNN, as we had before, I'm now replacing that one with a long short-term memory network. So when I've used Keras as an API together with TensorFlow, there is actually an optionality which is called the LSTM here. And I need to set up the number of hidden neurons and the type of activation functions, etc., etc. And I actually don't remember what this statement here means. I always have to look up the declaration of the variables. I'm going to look this up actually. And then there is also a so-called GRU network, a so-called gated recurrent unit, which we haven't discussed yet, which is another option to keep track of the long-range dependencies. And in this case, we can also run the network as we did previously. You see that compared with a simple case where we had 40,000 parameters, we are now getting into 675 something. And in this case as well, when I look at my loss function, this is actually getting a little bit better. And it's gradually getting closer and closer to what we got with a simple neural network. And in this case, I'm getting a slightly better prediction than I had in the case when I just took a simple RNN, and I had, instead of one hidden layer at each stage, I added another hidden layer. But even in this case, we are not faring that well with the prediction. And you can see now that the total mean squared error for all the mean squared errors is actually 2 orders of magnitude larger than the one we had for the simple case with only 40,000 parameters. So it's not given that a more sophisticated model will do well in the case you're looking at. So that means that one has to play around with different architectures. This is a kind of basic wisdom which you can extract from all the calculations we've done and all the analysis we've done with the convolutional neural networks, with the recurrent neural networks, and with standard neural networks. Now, these are all supervised learning methods. If you wish to move on a little bit and into the field of autoencoders, which is a very active research field, by the way, but I would suggest that we leave this as a topic for self-study. And these are also artificial neural networks, which are capable of learning efficient representations of the input data without any supervision. So often the data set is unlabeled. And these codings typically have a much lower dimensionality than input data, which makes the autoencoders as a kind of system or algorithm for dimensionality reductions. And you can, I put up some links in the beginning of the slides here, and there's actually a good link here to the original paper on autoencoders. I'm going to add material here, but I will not give lectures on it simply because it would require more time, and Anders begins on March the 28th. So I would suggest that we use the rest of the time now simply to work on project 2 before Anders takes over. So that means the next lecture, I will stop the recording now, and then after a small break, we can then just discuss and work on project 2, and Atle will be leading the discussions. And then next Tuesday, we do the same, so that you have time to discuss with your fellow participants and with Atle as well. So I will not do any lectures next week. So, and there will be no Zoom session which is being set up then. I'm going to stop sharing here, and I'm going to stop the recording.